Hello. Let's start my session. My session is AGL Instrument Cluster Expert Group activity, and that's research and practice to realize Linux containers that support embedded use case. It's my presentation detail. This slide shows my personal information. So my name is Naoto Yamaguchi from Aisin Corporation. I'm a member of AGL Instrument Cluster Expert Group since 2019. This slide shows today's session and presentation outline. At first, I share the background. It's Instrument Cluster Expert Group information and overview for target system and file user Linux container. Next section is technical issue sharing. So first point is a breakdown for my QM isolation. It's a ICEG basic architecture. Next one is the issue and knowledge for our development activities. At last, we will conclude this presentation. So, AGL Instrument Cluster Expert Group launched at 2019. Our motivation is create a best platform for instrument cluster, not a platform based on conventional IVI. Because there are different system requirements between IVI and the cluster. For example, functional safety require for instrument cluster side and need to quick boot up in instrument cluster side. So our second motivation is this platform is built from open source technology. That means need to independent from existing proprietary software components and need to be able to choose open source software component or proprietary software component. So this slide shows a generic system design for ICEG work. Instrument cluster and IVI into one system. Instrument cluster is required functional safety. Characteristics for the system. Connecting one or more displays, connecting the speakers, connecting the to phone by Bluetooth and USB and Wi-Fi, connecting the USB devices, and some sensor and another peripheral device connecting by the I2C, UART, SPI, and etc. And connecting to other in-vehicle ECU by CAN, Ethernet, and other connecting to parts. What are the product development issues? That answer is the quality and the robustness. Typical instrument cluster requires to the functional safety HLB. Because instrument cluster has telltale functions. And it shows critical failure information to driver. Next point is the quality management. They have a separate quality requirement between instrument cluster and IVI. Approach for functional safety. So our approach is main function is focusing. So main function is very function for our system, required advanced quality management, open innovation, and other requirements. On the other hand, safety function side ensures the vehicle safety. It has what function does it include? Which OS do you use? Which communication method do you use? These are highly dependent to your systems. Our approach is using the isolation method, separate main function and the safety function. That called the safety island approach. we are focusing to the main target for main function. So in main function side, paths between RBI and the instrument cluster, it's a big issue. RBI side required the rapid innovation, and that is a new feature added, short-term development, and rapid bug fixes. On the other hand, instrument cluster side required the advanced quality management. It's required to the full path coverage testing, formal verification, and carefully bug fixes. It's a big puzzle. One more puzzle is IBI requires various functions. Many pre-installed application is required, and the applications installed from store. It's a IBI side requirement. Another instrument cluster side, a selected function is implemented. It requires a combinational verification and fast boot up. It's a second puzzle. Our answer for these puzzles. One more isolation method using it. That means main function are isolated according to the QM level, boot time and incident type, etc. For verification side, selected software isolated full path coverage and verification. It's isolated from IBI. Rapid innovation side, IBI side. This architecture we call to the QM isolations. That means QM level isolation for each software stack. So we use this isolation method, Linux container. Its Linux container is an operating system level virtualization method. So running multiple isolated Linux system that calls the containers on a host using a single Linux kernel. It's a strong point. That technical point is isolate root file system on Linux kernel by using change root. Control resource by using the C groups. Hide resources from other containers by using the namespaces. And then Linux container strong point is easy to use in embedded environment because it requires only Linux BSP. No need additional virtualization driver development. And they can integrate it container-based system over hypervisor. So the next topic is a technical issue for our QM isolation approach. So point of QM isolation. First point is the software stack isolation. So instrument cluster side, build high quality assurance software. Will not change after SOP without critical bug fix. IBI side, built by standalone software, will change after SOP. So this two separate software stack can integrate it one Linux kernel. It's a Linux container strong point and our QM isolation approach. So next point is resource isolation. First one is computing resources. So quick response is required in instrument cluster container. It requires real-time scheduling. When all of the system built by real-time scheduling must protect instrument cluster computing budget from IBI. So this condition priority priority design is a true complexity. difficult to rapid innovate development in IVI container. So this means needed the computing resource isolation. Next is memory resources isolation. When all of the memory was allocated, new memory allocate request can cause both process kill or process deadlock in typical Linux system. It's a Linux kernel issue for embedded use case. So in this case, must protect instrument cluster memory budget from IVI. And this memory allocation issue need to be closed in the IVI. So computing resource isolation, how to realize? So CPU shielding based isolation using the C group CPU set. So it realizes isolated scheduling class for instrument cluster container. We can use real-time scheduling isolated from other containers. It's a shielding by CPU core. Memory resource isolation is this one. Memory budget guarantee using the C group memory. For example, cluster budget is a 1 gigabyte. IBM budget is a 2 gigabyte. Easy to set up using the C groups by Linux container runtime. And this Linux container strong point is easy to rebalancing its strong point against the hypervisor. So next is display isolation and sharing. It's a issue for our issue for instrument cluster EZ. Cluster and IVI have separate requirement. Cluster UI require to high frame rate, and IVI UI is difficult to control drawing timing for each IVI apps because IVI have many apps in runtime. So QM isolation selected separate composite architecture. This one and this one. It realized to isolated composite and frame update timing between cluster and IVI. Next point is hide resource from other containers. IVI container has connected and connectivity device such as Bluetooth, Wi-Fi, and LTE, and more. In server security point of view, this device should insert into container and hide to other containers. Device hiding most easy way to protect from illegal device accesses because other container can't access and can't find the devices. Network namespaces realize network device hiding, and the mount namespace realize character and blocks device hiding. These are background and point of the QM isolation architecture. So next is a technical issue for development. ICEG are working to realize this architecture, but this was got some issue. ICEG member work to fix some issues. Today, ICEG has 3 points of the issue. One is the computing resource isolation. Next is the device management issue, and finally is the display isolation and sharing. So computing resource isolation issues are our design goal, real-time capability, and the CPU core isolation. It's these two capability we use in one systems. Generally, one or more guests required to the real-time scheduling in our generic architecture. Instrument cluster required to real-time scheduling, and IVI required to real-time scheduling using separate requirement. Linux kernel already supported real-time scheduling. In container environment, it is possible to use the config RT group sketch that realize real-time budget control. This functionality provided by CPU of C groups. CPU core isolation is the most easy way for computing resource control in CPU core budget binding to guest container. It provides per container real-time proprietary design and not required to system-wide proprietary design because it's isolated by CPU cores. Because cluster normal priority thread is not blocked by a high priority thread. This normal and high priority is same of both of the real-time priority. This functionality provided by a CPU set of C groups. So initial configuration to realize design goal. Core assignment, core 0 assigned to the cluster, core 1 and 2 assigned to the IVA guest. It's abstracted design. So, and real-time budget allocation is a system-wide real-time scheduling parameter set to these two parameters. And the real-time budget distribute to each guest. So cluster guest parameter set to 25% because 25% of the CPU core of 4 cores. So I will just parameter set 50%. It's the same pattern of the core number of the cores. So evaluated to this design. As a result, first topic is the condition for evaluation. So Linux kernel using 5.10, it's use AGL IC hardware. Set CPU set and CPU parameters. And real-time inflate loop thread run in cluster guest to calculate CPU usage. So this table shows test case 1, set up parameter and result. So this parameter, previous thread same as previous thread defined parameter. As a result, so my goal is 100% usage in cluster side inflate loop, but result is limited 25% of the CPU usage. Why causes this result? I try to next test case. That is test case 2. This test case set full of the real-time budget on cluster side. IVA side 0% of the real-time budget. As a result, instrument cluster side inflate loop can use 100% of the CPU. Issue for this result. As an evaluation result, this function is managing budget per CPU, not all of the CPU. The maximum real-time budget of the C group CPU is 100%. Total of all guest budget must be set less than 100%. This one. When cluster just reduced to 100% budget of one CPU, other guests can use real-time scheduling. Can't use the real-time scheduling. It's an issue. So, new configuration to realize design goal. A new configuration is same assignment for the core in previous setting. Real-time budget is a system-wide is the same configuration, but I disabling the config RT group sketched because this configuration causes CPU budget group control and limit and set a limit to the all container budget all of the 100%. Other test case is the evaluation result. This configuration not set a limit for the container per container setting. In this case, so we can use 100% on the cluster side and the hardware side. This configuration is realized design goal. This key point is when we want to use the CPU set-based resource control, need to disable the configurability group sketched. It's a difference of the existing Linux container use case. It's a embedded specific use cases. And conclude of this computing resource isolation. Design goal is the CPU core isolation with real-time capability for each guest container. It gets an issue for existing real-time budget control was not match this design goal. We get a knowledge need to disable configurability group sketched in case of the CPU set-based computing resource isolation. In this case, we need real-time thread restriction need to use other parameters such as a PR limit. It's our knowledge of this development. Next is the device management. So embedded system requires many types of the devices. Defined design goal is enable sharing and isolation. That device use only one guest and shall not be used other guests. Example is a GPIO. That device is such is shared on each guest. That example is a GPU. That device needs a partially shared on each guest. This example is a display. And enable device detect. That device enables statically at the boot time. This example is a GPIO and a sensor and a GPU. That device enabled dynamically around the runtime. Most good example is USB devices. So most easy way for this issue. So using container runtime features. Currently, we use LXC. LXC is supporting static character and block devices. Simple character and block devices can share and isolated by that features. LXC has partially support capability for CCFS node-based static devices. That use the RO and RW directory bind mount to realize access control at the CCFS node. But that is only partially support. At least GPIO is difficult to support in only these functions. And the LXC has manual operation support for dynamic add and remove devices file into guest. It does not have dynamically device add remove detections. Only add and remove device file into guest. That function needed to support outside of the LXC. Most good example is the USB devices. These missing features need to support outside of the LXC. First example is the GPIO. This slide shows a setup procedure for GPIO without container. So input port, first step is write port number n to sysfs node, export node. After that, sysfs directory automatically created by systems. Output port case is the same as this point. And input port write direction into direction file. Output port case is write direction out to direction file. And the input case is a read port value from the value. And the output case is the write port value to value file. It's a GPIO drivers. So GPIO support design goal. Guest container can operate GPIO. Each guest shall not export GPIO port to avoid unauthorized export. Allowed guest can operate output GPIO port. Normal guest can read input GPIO ports. This means read only. When that input port needs to block read operation, it rears to by mandatory access control, such as SE Linux and SMAX. This slide shows a setup procedure for GPIO in container case. So write port number is the same as out of container case. And the direction is the same. This operation need to do host side. And the host side additional operation is arrow bind mount GPIO directory into guest in input case. But typically not needed additional operation for this because /sys directory is arrow bind mounted in guest launching time. Output port case need to RW bind mount GPIO directory into the guest. This RW mount operation must do after export. This one. This operation need to host side before the container launching. So conclude of this issue. Design goal is as shown. And the issue is this design goal requires some host side operation. It's I shows a previous slide. Knowledge of this development. So need to set up GPIO port before the guest launch. And the sys class GPIO directory is a symbolic link to the other sysfs path. For example, in AGL reference hardware case, real path is this path. So RW mount operation shall do that real path, this one, not this one. It's our knowledge of this development. Next is the USB support. USB is one of the complex devices for embedded use case because it uses many of the Linux driver subsystems. Character device subsystem, USB UART, audio input device such as the touch key and etc. And the block devices using the USB mass storage class devices, and the bus device, and the live USB based device using it bus driver, and the control devices CFS and the control config face. What technology is needed in USB device management for container? Create a device node to guest. It's a need to do. So dynamic device node creation into guest from host it can realize by reusing the libLXC features. That means it can reuse the LXC runtime. Another one is the dynamic device node creation in guest. So it can realize by add a CapMK node capability to guest. It's only a container configuration. So, and the next point is the notification device status to guest. It requires to send U event to guest from host. So LXD community developed U event injection feature for kernel. This U event injection detail, please refer to this slide and links. So we define the two solutions for the USB support. First one is the U event generation and injection method. So target device for experimental development is the USB master storage class block device subsystem. That design goal is a container management daemon, scan and monitor devices. That judge which device shall assign to which guest. That add device node into guest. That sends generate U event into guest. This operation by the container management daemon. So architecture is this solution. Management daemon scan and monitor block devices using the review dev. And the management daemon launch guest after the scan and the monitoring start. Management daemon judge all known devices which container is required. And the management daemon add device node into the guest. After that, management daemon generate U event by device information get from review them and injected this U event to guest. So after the launch, when new device is detected, management daemon update and judge device assignment. After that, typical case is create a new device file and send a new event. But in this point is this operation is asynchronous operations. It's a weak point for this solution. So issue of this architecture. U event generation is needed hard-coded one-by-one implementation. So because a U event monitor can get all information of the U event, but a U event scanning can't get all one requested information. Impossible to keep U event ordering because this solution is a U event generation, not a redirection. That information is independent from the other subsystems. It is not a reproduce U event order across subsystems. And impossible to generate other than add remove event because it's lost the ordering. And unable to synchronize when device management with device management feature in guest. Because U event notification start after a launch guest, but it's not waiting guest side device management to start. Device manager start. So consideration. Solution-wise, a match for simple dynamic device management. So only to support a USB master storage class. Only to support simple character devices. On the other hand, it's not much complex USB device management. That means that device require to ordering U event, bus device event, and master storage class device event. So solution 2 is a U-event redirection method. So target device for the experimental device development. So USB master storage class and USB bus driver. So design goal is this solution. So container management daemon monitor U-event, not scanning. That judge which event shall redirect to which guest, and that add device node into guest, and that redirect event into guest. So architecture of the solution 2. Management daemon monitor U event using the review dev. Management daemon launch guest after monitoring start. Management receives the U event, judge and the U event which container is required. After that, management daemon add device node into guest and redirect to the U event using the U event injection. This operation is a synchronous operation. That means it's real to keep ordering. So issue of this architecture cannot assign a device that is already detected because it's a redirection. It requires the notification of the new devices. Need to rescanning a USB device after the guest launch using bus power phone. That means redetecting using the USB driver. Unable to synchronize with device management in guest. It's the same issue of the solution 1. So consideration of this. Solution 2 is a much for complex dynamics device management. That can inject to guest other than out remove event. And this solution possible to keep event ordering. It's a strong point. On the other hand, it's required a complex judgment rule and that solution 1 to use a simple device. So conclude this design. Our goal is a USB device dynamic assign and manage it. So this analysis is a need to extra development to use a USB device in guest. Both solution has some issues. When the Linux system has USB rescan support, that means your Linux kernel has support the USB power off on or bus reset. Solution 2 is a better choice for this. So third is a display isolation sharing. But this solution is already informs some event. AGL and TechDay and ALS. And please refer to this presentation material. So how to realize this future? So ICEG is developing a container management demo. So it works with DRAM release manager. It's a previous DRAM sharing, display sharing method. It aims to support embedded use case and based on LibRxC from Rxc and it provides under the Apache 2 licenses. So currently, its development status is experimental development stage, but it's completely open source software and can get source code from this repository. And after the out of the experimental development, I will upstream in AGL Git. So finally, the conclusion. So about this presentation, in this presentation, talk about the AGL ICEG background and the target. Sharing current status, issue, and knowledge. ICEG uses Rxc for container runtime. It's a powerful container runtime engine to support library use. But it has some mismatch for embedded use case. ICEG development container management daemon to fix this mismatch. A part of that mismatch is already fixed by this development. And the future work is continue to develop that container management daemon to improve the embedded use case support. That's all from my presentation. Thank you for listening and attending. So, how to do a Q&A this virtual presentation case? So I can hear.
Is there someone who has a question, actually? From the audience, I have the microphone here, and I can just hand it over if someone has a question to put directly to Yamaguchi-san. I think it's on. I hope you can hear me, Yamaguchi-san.
Yes, I can hear.
Great. So if someone brings a question, then I have a question, maybe because we anyway run at the end of the time. If you see that you have a lot of device responsibility and you assign the third container, do you make any assumptions to say here's the third real-time container and this takes responsibility for devices to be shared to other containers, so that you use maybe virtualization hypervisor methods to run these also on containers?
Mm-hmm.
Yeah.
Yes, please.
Yeah. Or do you try to keep it more simple by saying we would like to split between two containers, the IVI and the instrument cluster world?
Your question is which point is simple of the device sharing? Is it okay? So in hypervisor case, need to develop a specific sharing device driver inside the hypervisor, and need to develop the driver for using the hypervisor side driver in the Linux kernel side. That means it need to require to the extra development for the virtualization driver. So on the other hand, Linux container case can use existing Linux kernel driver. It can same of the this one, but in display sharing case, need to extra development in our side in instrument cluster use case. It's a limitation for the DRM subsystem side, not the driver side, because DRM subsystem limited only one DRM master in one system, because DRM master managing to the resource of the display and the memory, device memory. But our use case need to two or more DRM master in one systems. That answer is DRM sharing. This feature is already implemented inside the Linux upstream Linux kernel. That name is a DRM release. So we created only management DRM release management demo, not created new driver. This DRM release manager is can use separate another SoC, not limited, not only Linux, Arca Gen 3 of the AGL reference hardware. It's a strong point of the Linux container architecture.
Then, thanks a lot. I guess we also have the next talk coming up, right? So thank you very much. And
thank you.
Have a good
if you have a question, this day we'll hold the ICEG BOF. Please, let's talk about this BOF. Thank you.